In section 3 of chapter 9, one of the concepts that's taught is how to figure out what the limiting reactant is in a chemical reaction. So that's what I'm going to go over right now. There are really two things that we have to do to figure out what the limiting reactant is. We have to be given two values in our problem. So far all the problems we've worked out, they've only given us one number, and from that one number we could convert it to different units of different compounds. With limiting reactants, they have to give us two values, and if you look at problem 25, they give you 2.5 moles of copper and 5.5 moles of silver. So in any limiting reactant problem, the first thing you have to do is convert both values of moles to moles of product. So so we're still doing T-charts, and anytime you do any of these T-charts in stoichiometry, we still have to have a balanced chemical reaction. So we have 2.5 moles of copper and 5.50 moles of silver nitrates in a single replacement reaction. Identify the limiting reactant. So we have copper metal plus silver nitrate, single replacement reaction, so copper and silver trade places, and we end up with the silver by itself, and then a solution of copper nitrate, and then we have to balance it, so we need a 2 here and a 2 there, and we're good to go. So to find the limiting reactant, the first thing we have to do is we have to take whatever values they've given us for reactants, and we have to convert that to moles of the same product. For this one, the product I'm going to pick is copper 2 nitrate. You could do the exact same thing, but you choose to convert yours to moles of silver. We'll still figure out what the limiting reactant is, and we'll get the same value. When it asks for an answer of limiting reactant, we have two reactants. Those are our options in our answers. Ag, CuNO32, those are products. Those will never be limiting reactants. So make sure you pay very close attention when you answer these questions that your answer is actually one of the reactants listed and not a product. So we need to take our 2.5 moles of copper and convert it to moles of product, and the product I've chosen is copper nitrate. So I have 1 mole of copper and I have 1 mole of copper nitrate. So real easy. Right, so if I have 2.5 moles of copper, I can make 2.50 moles of copper nitrate. Then, if I have 5.5 moles of silver nitrate, how much copper 2 nitrate can I make? So that's going to be my next step. I have to convert this to moles of copper nitrate too, so I can easily compare them. So looking at my balance reaction, I have 2 moles of AgNO3 and I only have 1 mole of CuNO32. So put that in your calculator. You get 2.75 moles of CuNO32. All right, so we did the first step. Our second step, We want to choose the smallest value, and the reason why, if I've given you 2.5 moles of copper, you can make 2.5 moles of copper nitrate. If I give you 5.5 moles, you can make 2.75 moles of copper 2 nitrate. So which one of these two reactants, copper or silver nitrate, keeps us from making the most amount of product? It's going to be the one that gives you the smallest result. So that'll be this top one. So this is my smallest answer. That's not my final answer because copper 2 nitrate is a product, not a reactant. So what we have to do when we write our answers, we have to say Cu, copper, is the limiting reactant. And we know that because it gave us the smallest value. So we get that from here. We go back and we look, this answer was the smallest, so we trace it all the way back to what we started with. All right, so anytime you have a limiting reactant question, you take both your values, you convert them to moles of the same product, and then you choose the reactant that gave you the smallest answer. So that's all we had to do for A, was identify it. Part B tells us determine the amount in moles of excess reactant remaining. All right, so if copper is our limiting reactant, then that means silver nitrate is our excess reactant. That means we're not going to use it all up. We're going to have some left over. So it wants to know how many moles are going to be left over. Well, to know how much is left over, first we have to calculate how much silver nitrate did we use. Well, we can only make 2.5 moles of copper 2 nitrate. We don't have enough copper to make 2.75 moles. So I'm going to start with 2.5 moles of copper nitrate, and I'm going to convert it to moles of silver nitrate. I look back at my balanced equation. 1 mole of copper nitrate gives me 2 moles of silver nitrate. Calculate that, it becomes 5 moles of AgNO3, and that's how much is used. So since we can only make 2.5 moles of copper nitrate, we're only going to use up 5 moles of silver nitrate. The question asks, determine the amount in moles of excess reactant remaining. So we calculate how much was used. To figure out how much is remaining, we have to subtract. It tells us we have 5.5 moles available, but if we look at our math here, we're only going to use 5 moles of it. So how much is going to be remaining? Well, real easy. 5.50 moles minus 5 moles. So we're only going to have a half a mole of AgNO3 left, or remaining. Okay, so that's our answer for B. Part C, determine the amount in moles of each product formed. right, so we need to figure out how many moles of silver we form and how many moles of copper 2 nitrate. We've already done copper 2 nitrate. We can use this answer right here, this 2.5 moles of copper 2 nitrate, since it's our limiting reactant. And so that one's already done. And you can just write that in on part C as one of your answers. So now we need to figure out how many moles of silver is produced. So we start with, we're going to use up all of our 2.5 moles of copper. If we look back up at our chemical reaction, for every 1 mole of copper, we use 2 moles of silver. We put copper on the bottom because we want to cancel it out. And we want silver on top because that's what units our answer should be in. So we get 5 moles of silver. If I have 2.5 moles of copper, I can make 5 moles of silver. All right, so that is all of C. Question D. Determine the mass of each product form. So C, we calculated moles. So now I'm going to take this value, this 2.5 moles of copper 2 nitrate, and convert it to grams. Different color. So we're on D now. We take 2.50 moles of copper 2 nitrate, and we want it in grams. So 1 mole of copper 2 nitrate. So now we have to look at our periodic table, and we're going to add up the mass of copper, 2 nitrogen, and 6 oxygen, and we'll put that in our calculator, and we get 187.57 grams of copper 2 nitrate. 1 mole on the bottom, because we know anytime we get a value from the periodic table, it's going to be equal to 1 mole. Part D asks how many grams of product. We have units of grams, and CuNO32 is a product, so we can stop. So punch that in your calculator. And we get 468.9 grams of copper nitrate. So now we have to do the same thing with silver. So if we can make 5 moles of silver, how many grams is that? So we're going to set it up the same way. There should be a decimal point in there. If we look up the mass of silver on the periodic table, it's 107.87 grams. And everything on the periodic table is equal to 1 mole of that substance. So now we plug this in the calculator. We get 539.4 grams of silver. So now we've answered all the questions. And this is something that you would actually do for lab. You could figure out, if I give you 10 grams of copper and 15 grams of silver nitrate, how many grams of silver can you make? How many grams of copper 2 nitrate can you make? So this is the whole reason why we do this type of problems, and why stoichiometry is so important in chemistry, is because we use it in lab on a very regular basis. You will be using it in lab as well. All right, let's do another one. Look at 28. Is all about percent yield, and this is another topic in section 3. They give you a formula. It's actual yield over theoretical times 100 equals our percent yield. Actual yield, this is a value that you get from your lab results. The theoretical yield is something that is calculated. So in number 28, they actually give you theoretical yields, Normally we could take answers from question 25. We could take our 539 grams of silver and say, okay, well, that's our calculated yield, that's our theoretical. And then if we went to the lab and we actually made some silver, that would be our actual. And then we could divide the two and multiply by 100 to get our percent yield. And that will be something that y'all will do. All right, so on 28, calculate the indicated quantity for each of the various chemical reactions given. So on letter A, they give us 20 grams is our theoretical yield. And we have 15 grams of our actual yield times 100. Put that in your calculator, or you can probably do that in your head. Gives us a 75% yield. So if we went into lab and you had to do an experiment, you were supposed to get 20 grams of product and you only came up with 15 grams, your percent yield is 75%, which means that your percent error is 25%. Letter B. They give us the theoretical yield and the percent yield, and we have to solve for the actual yield. So our theoretical is 1 gram, and our percent yield is 90%. So to solve for our actual yield, I'm going to put an X here to represent my actual yield. I'm going to take 90 and divide it by 100 and multiply it by my theoretical yield, or multiply it by 1 gram. And so for actual yield, you should get 0.90 grams. And for letter C, they give us our theoretical yield of 5 grams. Actual yield is 4.75 grams, and we have to calculate the percent yield. So our actual was 4.75 grams. Theoretical was 5 grams times 100. And you punch that in a calculator, and you get 95%. And then the last one, the theoretical is 3.45 grams. The percent yield is 48%. So we have to calculate the yield. Sorry, drop the microphone. All right, so we don't know what the actual yield is, so I'm going to put an X. 3.45 grams for my theoretical times 100 equals 48.0%. Those are terrible results. So 48 divided by 100 times 3.45, and our actual yield is equal to 1.66 grams. That's the answer for D. All right, so that is everything from chapter 9, section 3. On the second worksheet I've given you, there are a couple of problems where it asks for volume. And so that actually comes from some information that we got in chapter 3, where it says 1 mole is equal to 22.4 liters. And we only use this when we're talking about a gas. It also talks about STP. This just stands for standard temperature and pressure. So that means you're working at sea level, you're working in a regular lab room, you're not working in any kind of extreme conditions. So these are fairly simple problems. So if you turn in your textbook to chapter 11, it's actually on page 392. It's problem number 44. Acetylene gas, C2H2, undergoes combustion to produce carbon dioxide and water vapor. If 75 liters of carbon dioxide is produced, how many liters of acetylene are required? So again, the first thing we have to have is a balanced chemical equation. So acetylene, it undergoes combustion. So anytime we have a combustion reaction, it's a carbon compound plus oxygen gas, and always produces carbon dioxide and water. So then we have to balance it. Let's see, we need a 2 there, a 2, and a 5. All right, so we have 75 liters of carbon dioxide, so we know automatically we're going to start with that. It's the only number they've given us. And we have to figure out how many liters of acetylene that's going to produce. So we have units of liters. The only thing we can do with liters is 22.4 liters is equal to 1 mole. Since we want liters to cancel out, we're going to put 22.4 on the bottom. So we have to put 1 mole of CO2 on the top. All right, we've got our answer in moles. So now we can do a mole ratio. So for every 4 moles of CO2, we get 2 moles of acetylene. I have to put my 4 moles of CO2 on the bottom so that it cancels out. And it wants our answer in units of liters. Right now I have my answer in moles. So I need another box. And we're going to use our conversion to go from moles to liters. So 1 mole is equal to 22.4 liters. I have to put 1 mole on the bottom so that it cancels out with the moles of acetylene from here. And I'll put my 22.4 liters on the top because that's what I want to end with. All right, so my units match, my compound matches. I can now use my calculator. So we multiply all the numbers across the top and get an answer. Multiply all the numbers across the bottom and get an answer, and divide those two values. And you should get 37.5 liters of acetylene gas. And these are a little bit faster than the other problems because we don't have to add up molar mass from the periodic table. So they seem to go a little quicker. Letter B, what volume of H2O vapor is produced? So again, we'll just start with our 75 liters of carbon dioxide. Right, since we have liters, the only conversion we know about liters is 22.4 is equal to 1 mole. So I'm going to put 22.4 liters on the bottom so it'll cancel out. And I'm going to put 1 mole on top. Since I now have my answer in moles, I'm going to go back to my balanced equation and I'm going to do a mole ratio. So for every 4 moles of CO2, I have 2 moles of H2O. I'm going to put my 4 moles of CO2 on the bottom so that it cancels out. And I'm going to have 2 moles of water on top. Let's see, the question asks for it by volume. So liters is our unit for volume. So I need another box. I can't leave my answer in moles. So again, I have to do moles to liters. We know that there's 22.4 liters in 1 mole. So I put my 22.4 on top. I put 1 mole of water on bottom so that it cancels out with my other moles. And now I have the correct units of the correct compound, so I can stop drawing boxes. And I can plug this in my calculator, multiply across the top and get an answer, multiply across the bottom and get an answer. And you should also get 37.5 liters of H2O. And then letter C. What volume of O2 is required? So we're going to set up the exact same set of T-charts, but this time we're going to use oxygen gas. Still got to use our 22.4 liters so that it cancels out. We're going to look at our balanced chemical equation and see what our mole ratio is. So for every 4 moles of CO2, we get 5 moles of oxygen gas. I'm going to put my 4 moles of CO2 on the bottom so that it cancels out. And put 5 moles of oxygen on top. And it wants to know what volume of oxygen gas is required. So again, that's units of liters. So we know that there are 22.4 liters of any gas in 1 mole. So my answer is in liters. It's also in the correct compound of oxygen. So now I can multiply across the top, get an answer. Multiply across the bottom, get an answer. And divide the two values. And you should get 93.8 liters of oxygen gas. All right, I'll do one more set of problems on volume. So if we look at problem number 45, assume that 5.6 liters of hydrogen gas at standard temperature and pressure reacts with excess copper 2 oxide according to the following equation. Make sure the equation is balanced before beginning your calculations. If we look, the equation is balanced, so we don't have to do that. How many moles of H2 react? Well, start with the number they give you in the problem. We have liters. The only conversion factor we know about liters is 22.4 liters is equal to 1 mole. So I'm going to put 22.4 liters on the bottom. 1 mole of H2 on the top. Once you get your answers in moles, you need a mole ratio. So, oh wait, it says how many moles of H2 react. We've got moles, we've got H2, so we can stop. We don't need another box. I was getting carried away. Right? So you can set this up in your calculator, and you should get 0.250 moles of H2. That was easy. All right, letter B. How many moles of Cu are produced? Well, the easiest conversions to do are always moles to moles. So, since we have an answer already in moles, we can start with that. So for B, we're going to start with our 2.50 moles of H2, and it wants to know how many moles of Cu are produced. So since we have moles of H2, the next step is a mole ratio. So for every 2 moles of H2, we have, for every 1 mole of H2, we have 1 mole of copper. So 1 mole of H2 on the bottom, 1 mole of copper on the top. We've got the correct units for the correct elements, so we can plug this, and then we get 2.50 moles of copper. Easily done in your head, but remember, you've got to show the work. I've got to see that this made sense to you in your head. And then part C, how many grams of copper are produced? So in B, we calculated moles, so now we need to take that number of moles and change it to grams. So we can start with our 0.250 moles of copper, and we'll go to the periodic table. We know that 1 mole of copper is 63.55 grams. So we multiply that out and we get 15.9 grams of copper. Great. So you'll need information from this problem and the previous one to be able to do the second stoichiometry worksheet.